GeopByte.
Hello friends, welcome to the GeopByte. In this video, let us discuss some very important problems which were already given in the previous ECET exam. These are all the problems from strength of material. Since the each and every problem is equal important, you please watch till the last problem. While you are listening the problem, if you find any difficulty, you please send your question to the GeopByte. Definitely the GeopByte team will answer all your questions within 24 hours. After listening all these problems, you please try to practice with pen and paper. Practice is very important to get the single digit rank in any competitive exam. Look at the very first problem. In the stress strain diagram for mild steel, which one of the following represents the point where the strain increases without increase in stress? Dear friends, once the body reaches to the yield point, look at the stress strain diagram. If you apply the external force on the mild steel bar, it comes like this. This is the point called yield point. At that yield point, even if you apply minimum amount of force or minimum stress, the body goes to deform continuously. So even if you apply very less load at the yield point, the body starts to maintain huge amount of strain. Therefore the answer is yield point. Let us read the problem once again. In the stress strain diagram for mild steel, which one of the following represents the point where the strain increases without increase in stress? That point is called yield point. I hope you got my point. Let us take another problem. Look at the second problem. A rod is 2 meters long at a temperature of 30 degrees centigrade with one end fixed and other is free at a distance of 1 mm from the rigid wall. If the temperature of the rod is raised to 100 degrees centigrade, the stress experienced by the rod, considering alpha equal to 12 into 10 power minus 6, it is given like this. One end is fixed, other end is free at a distance of 1 mm from the rigid wall. It is like this. This is the one fixture. This is your body. The length of the body is given 2 meters. Okay, then initial temperature T1 equal to 30 degrees centigrade. Other rigid wall is placed at a distance of 1 mm from the rod. This gap is 1 mm. That gap is 1 mm. By the time the temperature is increasing from T1 to T2, that T2 is given 100 degrees centigrade, definitely body is going to elongate. Coefficient of linear expansion of the body alpha is given 12 into 10 power minus 6 per degree centigrade. You are asked to find what kind of stresses are developed in the rod. Dear friends, since the gap between the rod and rigid fixture is 1 mm, if the extension is more than 1 mm, the body can reach to the rigid fixture. Once it reaches to rigid fixture, the rigid fixture tries to oppose the further expansion of the rod. Therefore, compressive stresses are developed. But if the extension is less than 1 mm, no thermal stresses are developed, because as long as the thermal expansion is free from any restriction, no thermal stress are developed. For that, first let us find the change in length. Change in length due to temperature change is L into alpha into dt. This is the formula. L is how much? 2 meter, that is equal to 2000 mm. So 2000. What is the alpha? Alpha is given 12 into 10 power minus 6 multiplied by dt 100 minus 30. You simplify this value for getting how much elongation is happening in the body while the temperature is increasing from 30 degrees centigrade to 100 degrees centigrade. So the change in length or extension is 1.68 mm. That means the body is going to elongate for a distance of 1.68 mm. Since the rigid fixture is available at a distance of 1 mm, that means 1 mm distance the rod is freely expanding. Once it reaches to rigid fixture, the rigid fixture tries to oppose the further expansion of the rod. Therefore, compressive stress are developed in the rod. I hope you got my point. But remember, if the change in length is less than 1 mm, no thermal stress are developed. In that case, you can select the option C. Anyhow, I hope you got my point. In this case, the required sufficient space is not available for free expansion. That's why the compressive stress are developed in the rod. I hope you got my point. Let us take one more problem. Look at the next problem. The maximum deflection of fixed beam of span L carrying a concentrated load W at the center is, it is like this. A fixed beam is there. That fixed beam is fixed between the two supports, two fixtures. The load may be acting at the center like this. Length of the beam is this one. Then the beam is going to deflect like this. The maximum deflection, remember, for the fixed beam subjected to point load at the middle of the span is WL cube by 192 EI. Remember this formula. That is the maximum deflection expected from the beam when it is fixed at its both ends. Therefore, option 2, second option is absolutely correct. I hope you got my point. Let us take another problem. Look at the fourth problem. The point of contraflexure in beams is the point where the, dear friends, the point where the bending moment diagram changes its sign from negative to positive or positive to negative is called point of contraflexure. The point of contraflexure is generally occurring in the overhanging beam. At the point of contraflexure, bending moment value is 0. Look at the options. The point of contraflexure in beams is the point where the bending moment is 0, shear force is 0, bending moment changes its sign. Absolutely correct. Bending moment changes its sign from negative to positive or positive to negative is called point of contraflexure. Of course, bending moment is 0 at the point of contraflexure, but most appropriate answer is C. That's why I select the third option. I hope you got my point. Let us take another problem. Look at the fifth problem. The deflection at the free end of a cantilever beam of length L, moment of inertia I, and modulus of elasticity E when subjected to uniformly distributed load of W per meter is, it is like this. There is a cantilever beam is subjected to uniformly distributed load. The load is uniformly distributing W Newton per meter. The length of the beam may be L. Then the maximum deflection at the free end is equal to WL power 4 by 8EI. This is the standard formula. You try to remember this formula. When cantilever beam is subjected to uniformly distributed load throughout its length, maximum deflection is occurring at the free end with a magnitude WL power 4 by 8EI, where E be the Young's modulus, I be the moment of inertia, L be the length of the beam. Look at the fourth option. Fourth option is absolutely correct. I hope you got my point. Let us take one more problem. Look at the sixth problem. In a beam where shear force changes sign, the bending moment will be. Remember, wherever the shear force diagram changes its sign from maximum. Look at the sixth problem. In a beam where shear force changes sign, the bending moment will be. Dear friends, wherever the shear force diagram changes its sign from negative to positive or positive to negative, there you will expect the maximum bending moment. I hope you got my point. Wherever the shear force diagram changes its sign from negative to positive or positive to negative, you can get the maximum bending moment. Therefore, third statement is absolutely correct. Let us take one more problem. Look at the seventh problem. The force which meets at one point and their lines of action also lie on the same plane is known as, it is like this. At a particular point, all the forces may be meeting like this. Since all the forces are meeting at a particular point, that kind of force system is called concurrent force system. That too, it is given that all forces are on the same plane. Since all the forces are acting on the same plane, it is coming under coplanar forces. So, since all the forces are on the same plane, it is coplanar, and are meeting at the same point, it is concurrent. The answer is coplanar and concurrent forces. I hope you got my point. So this may be the force F1, this may be the force F2, F3, F4, F5, F6, F7, etc. I hope you got my point. Let us take another problem. Look at the eighth problem. If the value of Poisson's ratio is 0, then it means, remember, at the diploma level, if the Poisson's ratio is 0, such kind of material generally treated as the rigid material. Therefore, the first statement is absolutely correct. Remember, for the rigid material like cork ball and stone, the Poisson's ratio is 0. I hope you got my point. Let us take another problem. Look at the ninth problem. When a simply supported rectangular beam subjected to transverse downward load, the maximum compressive stress developed. It is like this. The beam may be initially like this. This is the axis of the beam. It may have the supports and the load may be acting like this. These are all the loads. Because of this load, what is happening? The beam is going to bend like this. The beam is bent like this. With respect to neutral axis or central axis, the upper layer is subjected to compressive stress. Upper layer subjected to compressive stress, and the bottom layers, also called as down layers, are subjected to tensile stress because tensile force is acting in the down layers. So this is the region where the tensile stress are developed. That too maximum tensile stress is developed at the bottommost layer. At bottommost layer. At bottommost layer. Maximum tensile stress are developed. Maximum tensile stress developed. Similarly, this is the compression zone. Compression zone. Maximum compressive stress are developed at the uppermost layer. This is the layer where the maximum compressive stress is developed. Compressive stress is developed. Now let us read the problem. When a simply supported rectangular beam is subjected to transverse downward load, the maximum compressive stress developed at the topmost fiber. Therefore, third statement is absolutely correct. Third option is absolutely correct. I hope you got my point. Let us take one more problem. Look at the last problem. When a load on the free end of a cantilever beam is increased, failure will occur. Dear friends, when the cantilever beam is subjected to load at the free end W, the maximum bending moment is occurring at the fixed end. Let this is the A, this is the B. Bending moment at A equal to 0. Bending moment at B equal to load multiplied by distance. Load multiplied by distance, W into L. This is the maximum bending moment. When free end load is increased, when free end load is increased, the maximum bending moment at the fixed end increases. At the fixed end increases. Wherever the maximum bending moment is there the chance of failure is more. At the section of the beam, where the bending moment is maximum, chances of failure are more. Chances of failure are more. Wherever the bending moment is maximum, chances of failure are more. So for this case, when you increase the free end load, definitely bending moment increases at the fixed end. Since the bending moment will increase at the fixed end due to increase in load, therefore chances of failure are more at that fixed end. So let us take the options. At the free end, no. At the fixed end, absolutely correct. The second option is absolutely correct. I hope, my dear friends, all of you clearly understood. You try to practice all these problems once again. If you find any difficulty, you please send a message to the GeopByte. GeopByte team will answer all your questions within 24 hours. Thank you very much. Have a great day. Please subscribe our channel called GeopByte. Best of luck. Thank you very much.
GeopByte.